to evaluate limits when you have the graph of a function, but more so what we want to do is get an intuitive understanding of what a limit is and what it is trying to communicate. So the first thing that I want to go through before we even start doing these sets of exercises here is to sort of understand what kind of operator we use whenever we talk about a limit and what that really is trying to communicate. So whenever we talk about the limit of a function in general, you're normally going to see this notation here. The main thing that we want to remember is that limit equals behavior. Okay? So when we say we want to know what the limit of a function is at a certain x value, or we want to know what the limit is as an x value approaches positive infinity or negative infinity, what we're really saying is, hey, let's study the behavior of that particular function as it approaches that x value or as it approaches positive or negative infinity. To be more specific, what we're saying is that, hey, as the x values get closer and closer and closer and closer to, let's say, this value a that's here, and we're looking at it from both directions, both from the left and from the right, we want to know as the x values get closer to that value a, what do the y values of that function start to approach? And so by looking at it that way, one clear distinction that we have to make in between the limit of a function versus evaluating a function is that when we study the limit of a function at a particular x value, that particular function does not necessarily have to be defined at that particular x value. So for instance, let's say I have this function here, x minus 3 divided by x plus 2. So one of the things that we know is that if I want to study the behavior of this particular function, meaning what does this graph look like, and as let's say its x value is trying to approach negative 2, okay? Well, we know from just knowing about finding the domain of functions, this particular function is not defined at x equals negative 2, because if I plug in negative 2 here in the denominator, that will make the denominator 0. And we know that anything divided by 0 is undefined. So in that sense, when we evaluate this particular function at 2, we know that we're going to get what's called an undefined result. But that does not also tell us what the limit of the function is. Remember, limit of a function is the actual behavior of the function. And it turns out for this particular function here, what you actually have is a vertical asymptote at x equals negative 2. And just in short, to kind of give you a quick sketch of what that graph may look like, this graph would look something like this, where it kind of goes like that here, and let's see, it will do something to this effect like that. And you'll have a horizontal asymptote here at y equals 1. And so we see at this vertical asymptote right here, which is at x equals negative 2, if we're studying the behavior of this particular function as we approach negative 2 from both the left and right side, we see that on the left side of this vertical asymptote, it goes up to positive infinity. On the negative side, on the left side, it goes up to positive infinity. On the right side, it goes down to negative infinity. So since the behaviors going up and down aren't the same, and on top of that, we can't answer this particular question of limit of this function with a real number, we would say that it is a case where it does not exist. And as I go through these examples, you'll kind of see when we need to say that and when we don't. The main thing that I'm trying to get across here is that when we talk about the limit of a function, we're talking about behavior of a function. As the x values get closer and closer to this value, what do the y values do? And when we say what do the y values do, is the same thing happening, in other words, on both sides of that particular x value. Is my function approaching the same y value? Is it approaching a different y value? Or is it going to positive or negative infinity? And so that's what we want to keep in mind as we go through these examples here. Now, in my opinion, the best way to be able to have a good foundation for understanding limits is to be able to understand how to graph basic functions. And so you'll see that I'll have a variety of algebraic functions here that I've graphed. If you're wondering, how do I graph all these particular functions without needing a calculator to do it, especially whenever we get into exponentials, logarithmic functions, rational functions, I do have videos on those as well, and I'll mention what those videos are as we go over those examples. So I just want to start off with that before we begin looking at these examples here, so you can kind of understand the context in which we're using this limit operator to be able to communicate what is the behavior of a function at a particular x value. So now I'm going to go ahead and clear everything out, and then we'll actually start. Okay, so let's go ahead and start with our first two examples here to the left. We have the function y equals 2, which is just a horizontal line. And what this particular limit is asking is, what is the behavior of the function y equals 2 as x approaches 0? And when we see it like this, what we really mean is as x approaches 0 from both the left and the right. And to be specific on what I mean by that is, we know here this at this particular point, this is the point 0, 0. So that means x is going to be 0 here. What we mean is, from the left, we mean as the numbers get closer and closer to x equals 0 from this way. So if we were looking at this on a t-chart, what we would say is something like this. Let's figure out what is the y value when x is negative 0.1. And then again, what is the y value when x is 0.01? And then what is it again when x is 0.001? And then do you see how we get closer and closer and closer and closer to 0 coming from the left side? When we say from the right, we mean just the same thing. But now let's say we're looking at it as we start at 0.5, and then we go to 0.1, and then we go to 0.01, then we go to 0.001. So when we mean as x approaches 0 from both the left, we mean looking at x values as we get closer and closer to it. In this case, from negative 0.1, negative 0.01, negative 0.001, as we get closer and closer to 0. And from the right, we're just getting less positive until we get to 0 for those. And so this question says, when my x values get closer and closer to 0 from both the left and the right side, what are my y values doing? Well, fortunately for this function, it's relatively easy here. It does not matter what x is, y is always 2. And we see here at x equals 0, that's the same coming from both the left and the right. So the answer to this particular question would just be 2. Because, of course, it's a horizontal line. As x approaches any number from both the left and the right, for this particular function, the y values will always be 2. And note that this is a situation where we know that at f of 0, it would be 2. In other words, this function is defined at x equals 0. One of the things that I had mentioned earlier is that in order to evaluate the limit of a function does not necessarily have to be defined there. But it does not mean that if it is defined, we can't evaluate it. So this is one of the simple cases. Now, this particular limit says, what is the behavior of the function y equals 2 as x approaches negative infinity? In other words, as x gets smaller and smaller and smaller from a negative perspective, what are the y values doing? Again, since this is a constant function, we know that that result is still going to be 2, because no matter how small my numbers get from a negative standpoint, my y values always approach 2, no matter how it looks. All right, so let's move on to the next example here, where we are looking at this line. And so now what we want to do is study what is going to be the limit of the function 2x minus 3 as x approaches 3. And if we say that with all the extra that's implied in that, what we're saying is what is the behavior of this particular function as x approaches 3 from both the left and the right side. So of course, coming from the left side, we're talking about, well, what happens when x is 2.9 or 2.99 or 2.999, okay? And on the coming from the right, we're saying what happens when x is 3.1, 3.01, 3.001, and it gets closer and closer that way. What are the y values doing when x approaches that? Now, if we look on our graph here, and we're looking at these as divisions of 1 unit, right here would be where x equals 3 is. And what we're studying is, as these values approach 3 from both the left and the right, what are the corresponding y values doing? And you see here that at this particular point, where this particular function is defined at x equals 3, we see that we have a result here of 3. Now, the reason why that is because the y values, as we get closer and closer to that point, the y values get closer and closer to 3, okay? It just so happens that in this case, that 2x minus 3 is a function that is defined at x equals 3 as well. So what the limit of the function is actually also ends up being what the y value for that function is at x equals 3. But again, note that for these functions, it is not necessary for the function to be defined at the value that we're trying to study the behavior on. Okay. All right, so if we look at this next limit, it says, what is the limit of our function 2x minus 3 as x approaches negative infinity? So when we look here, we see that as x gets more and more and more negative, the y values here get more and more and more negative as they go down like this. So the answer to this question would be negative infinity, okay? Now, one thing that I do want to say here is that anytime we evaluate a limit and the limit of the function, we can't answer that with a real number, then technically the limit does not exist. And we just put D and E for short. However, remember that when we ask about the limit of a function, what we're really trying to do is give the best depiction of the behavior of it, okay? And although technically speaking, I could take this example that's here, erase this right quick. I can take this example here and actually say that the limit does not exist, but that's not the best answer for what the limit is actually trying to communicate. What the limit is actually trying to communicate is, how does my function act as x gets smaller and smaller and smaller from a negative standpoint? So as the x values get more and more negative, we're saying that the y values get more and more negative. And that's a better way of describing the behavior of the function. We reserve this does not exist case for instances where the behavior from the left may not necessarily be the same as the behavior from the right. Or if we have a situation where, let's say our function is one-sided and the behavior, let's say from the left, looks like this, but the behavior from the right, the function is not defined. There's nothing there. So since there's nothing there, when we study the behavior of a function at a particular x value from both the left and the right, we can't give an answer because we have no kind of behavior happening from the right side, okay? And so we'll see some examples of that as we go through. go through this particular video. But I just wanted to try to pepper those things in, and hopefully as we do more and more of these, this will start to make sense. Again, the key to this, in my opinion, is that if you know how to graph these basic functions, and you know what the graphs look like, and you understand that limits equal behavior, then all this stuff starts to make a whole lot of sense. All right, let's move to the next page. So the next function that we're going to talk about is y equals square root of x plus 3. Okay, and so we see that this function looks like a square root function, but it is shifted over 3 units to the left. And we know that from graphing transformations from college algebra or pre-calc. Now, what we want to do is study the behavior of this function at a couple of x values. So we start off here with this limit, and what this says is I want to know what the behavior of this particular function is when x approaches -3, but this plus here means that we only want to study it from the right side. Okay, so what do I mean by that? In terms of the x values, I want to study as x gets closer and closer to -3 coming from the right. So if I'm looking at that from a negative standpoint, of course, this would be -1. This would be -2. And of course, here would be -3. So we're looking to say, hey, what happens when x is -2.5, and then 2.6, and then -2.9, and then -2.99, and then -2.9999. So we're saying, hey, as the x values get closer and closer to -3 from this standpoint, what are the y values then? Okay. Now, I'm going to go ahead and erase this. Here's our point here. Now we see as x gets closer and closer to -3 here, the y values, if we started to plot these points here, the y values are starting to get closer and closer and closer to 0. Okay, and of course, this is another situation where the function is actually defined at the x value that we're talking about. So it kind of makes it easy here. So the answer to this question is going to be 0. So as the x values get closer and closer to -3 coming from the right, the y values get closer and closer to 0. Now, if up here we said, what is the behavior of this particular function as x approaches 3 from the right, then of course, this must mean what? Yep, that's right, from the left. And so we're doing the same thing, but now we're looking at everything coming from the left side. Okay? So now to make my point, if we're coming from the left side, we're saying, well, what happens at -4, and then -3.5? And then -3.1, and -3.001, so on and so forth. If we look at our function here, what we start to see is that this function is not defined for values that are less than -3. So because of that, we have to answer this as does not exist, because there's no behavior to study. All right, so now what you see is we want to study the limit of the same function, but now whenever you don't see the plus or the minus in the exponent area, what that means is just like how we did on the previous set of examples, we're studying the behavior from both the left and the right, okay? And the idea here is that in order for us to be able to answer this with a real number or plus or minus infinity, we have to have the function doing the same kind of thing, acting the same kind of way, or going to the same kind of y value from both the left and the right side of the number. Now, for this answer here, in order for the limit from both the left and the right side of this number to actually be able to be answered with a real number or plus or minus infinity, this and this have to be the same, meaning that the limit from the left has to be the same as the limit from the right. And of course, since in the case of studying the limit of this function as x approaches -3 from the left, it does not exist, by default, that makes this limit does not exist as well. Because again, we're trying to study behavior of our function from the right, and we see that it goes to 0. But from the left, there's not anything there. So the behavior from the right and the left of x equals -3 is going to be does not exist, because the behaviors are not consistent. All right, so hopefully that gives you a good idea of what it means whenever we talk about the limit of a function from both the left and the right, and how everything has to be consistent to be able to answer it with a real number or plus minus infinity. Now, for this last example for the function square root of x plus 3, we see that, again, we're studying what is going to be the behavior of this particular function as x approaches 3 from both the left and the right. So here we are at x equals 3, and we're trying to study what is the behavior from both the left and the right, okay? Now, of course, if we do that, then we see as we get closer and closer to, let's say, this point here, from the left, we have these points. From the right, we have these points. And since 3 is in the domain of this function, we can easily find this by just plugging in 3 here. And of course, that would just end up being square root of 6. So that would be what the y values would be approaching in this case. Okay. Now let's move on to this logarithmic function. So we have log base 2 of x plus 3. So this is our basic log function, which in general looks like this. But we know that this plus 3 means that our entire function is shifted over 3 units to the left. Hence why we have a vertical asymptote here at x equals -3 instead of x equals 0 for the y-axis. So we look here and it says, hey, tell us the behavior of this particular function as x approaches -3 from the right, okay? And so from the right means that we get closer and closer to -3 by saying what happens when x is equal to -2.9, -2.99, -2.99999. Okay, so as we do that, we see as x gets closer and closer to -3, the y values get more and more negative, and they just keep dropping. So in this case, the behavior of this function is going to -infinity. Okay, so as x gets closer to 3 from the right, the y values get closer and closer to -infinity. Now, if we look at this same function coming from the left side, because that's what this symbol here means, give me the behavior of this particular function as x approaches -3 only from the left. Again, from the left of -3, we see that we have no graph. So since we have no graph, there's no behavior. And since there's no behavior, I would have to put does not exist as a result. Okay. Now, if we look here, this is also asking us the behavior of same function, but now as x approaches -4 from both the left and the right. And with here, we have the same issue with this limit as we do with the one that we previously did. Because again, here is where x equals -4 is. And if we're studying the behavior from both the left and the right of it, immediately from the left and the right of x equals -4, we still don't have a graph. So there's no behavior. So thus we have to put does not exist as the result. Now for the last one for this logarithmic function here, we want to study the behavior of this function as x approaches 1 from both the left and the right. And remember, whenever we don't have the plus or the minus in the exponent for this, then we know that it implies that we're studying the behavior from both the left and the right of that x value. and that the behavior has to be the same in order for us to be able to answer with a real number or plus or minus infinity. So in this case, we know that here's where x is equal to 1 is here. And of course, as the x values get closer and closer to 1, the y values look like they're getting closer and closer to 2. So in this instance, the answer to this would be 2. And just like how we did for this problem here, in the case of where the x value that you have, if this x value is actually in the domain of the function and this function is continuous, then we could literally just plug in this x value into here. So if we did that, that would be log base 2 of 4, because 1 plus 3 is 4. And log base 2 of 4 is just like asking what is the exponent for the exponential number that has a base of 2 and its result is 4. And of course, we know that 2 raised to the 2 is 4. So that is why the answer to that is 2. All right, so now let's look at this last set of examples. Well, not last set of examples, but next to last set of examples here. So now we're dealing with an exponential function, okay? And so same sort of thing. We're trying to study the behavior of the function as x approaches some value. So we look here, the behavior of this function as x approaches negative infinity. So if you notice, as x approaches negative infinity, so as the x values get more and more negative, if you notice, the y values for the points on the graph of this function are getting closer and closer to this line that you see right here. And this line is what is called a horizontal asymptote. And in particular, this line is the line y equals 2. Yeah. Yep, it's y equals 2. I was looking at it, I thought it was y equals 1, but it's actually y equals 2. So here, the result of this would be 2, meaning that as x gets more negative, your y values are actually getting closer and closer and closer to 2. For this exponential function, one of the things that we know is that that exponential function will never have a point that has a y value of 2, but the points as the x values get more and more negative are going to get closer and closer to y equals 2. Now, if we look in the other direction, what is the behavior of the same function as x approaches positive infinity? Well, as x gets more positive this way, the y values just tend to get higher and higher and higher. So in this case, we answer the question with positive infinity. And although technically this limit does not exist, the best way to describe the behavior is to say that as x goes to positive infinity, x goes to positive infinity, y is also going to positive infinity because the graph just keeps going up and up and up and up. All right, so now we look at the same exponential function and we want to study the behavior as x approaches 1 from both the left and the right. And so I'm going to erase some of this business here. Here's where x equals 1 is, and we see that as x approaches 1, these y values are going to be approaching 2. Okay? And so, of course, this makes sense again because 1 is in the domain of this function, and this function is nice and continuous, meaning we don't have any breaks, holes, gaps, or jumps in it. So here, literally what we could have done here, of course, we're going to answer it with 2, but we could literally just plug in the 1 here in this case. And we know that 3 raised to the 1 minus 1 is the same as 3 raised to the 0. And sorry, that's not 2, that's 3. My apologies on that. Having a hard time seeing this. So this is y equals 2, and this is y equals 3. So it's actually approaching a y value of 3 here. We'll see that from the calculations. Of course, Any non-zero number raised to the 0 power is 1. So that's how we get 3 raised to the 0 is 1, and 1 plus 2 is 3. And so again, we know that the behavior of this function as x approaches 1 from both the left and the right is going to be approaching a y value of 3. Again, I'm sorry about getting that confused with 2. All right, so for, one other thing I do want to say. So this situation here, whenever we have the limit of some function, as x approaches, let's say, positive or negative infinity, and we get positive or negative infinity as an answer, that is a form of what you call in pre-cal or college algebra in behavior. Same deal here. Whenever you have the limit of a function as x approaches positive or negative infinity, and you actually answer it with a real number, then what you actually have there is a horizontal asymptote. So for these next two, we are looking at this rational function here, and what I'm showing here is that for this rational function, if we simplify it, we see that this rational function is acting just like the line y equals -2, but we know that we cannot have that particular function be defined at x equals -2 because of what we see here. Okay, we know that will make the denominator 0. So literally, this particular function acts like a line with a hole in it, and that hole is going to be here at x equals -2. Now, here's a situation where I was talking about where the function, this particular function, is undefined at the x value -2, but we're going to be able to answer the limit of this function with a real number. And here you can see that the way this function behaves as x gets closer and closer to -2 from both the left and the right side, we see that the y values are approaching a value of -4. Okay? So although the function isn't defined at x equals -2, the behavior of the function is acting like it's going to the point -2, -4, and hence we know that the limit of this particular function as x approaches -2 from both the left and the right is -4. Now for this example, we know as x approaches negative infinity for the same function, as x gets more negative, the y's get more negative. So again, we can answer that as just negative infinity. All right, so with our last set of examples here, we have this rational function. And again, if you don't know how to take a function that looks like this and graph it without needing a calculator, please check out my videos that I have, graphing rational function examples. I have 6 of them. And you can just look under my name, Valdez Gant, and Empowered Learning. You'll see it either way. So for this example here, we're studying what's happening to this particular function as x approaches positive infinity. And like we talked about before, we want to know what is the end behavior of the function. Well, as x gets more positive, do you see how the y values are getting closer and closer to this horizontal asymptote, which is y equals 1. So the answer to that is just 1. Now, if we look here, we want to study what is the behavior of this function as x approaches 2 from both the left and the right. And if you notice here at x equals 2, we have a vertical asymptote here, okay, which is like a discontinuity where the function either tries to go below the wall that's created by that imaginary vertical line or climb above it. In this case, do you see as x approaches 2 from both the left and the right, the y values for each of these functions keep going down to negative infinity. And since on both sides of x equals 2, the function is doing the same thing, meaning that it's going down to negative infinity, the best answer that we give for this is negative infinity. And like I said before, it is technically true that the limit does not exist, because a limit does not exist whenever we can't answer a question about a limit with a real number. However, the best way to describe the behavior is with negative infinity, because we see that both from the left and the right side of x equals 2, the function does go down to infinity. Okay. All right, so for our last function, we have a parabola, and this is a parabola that is in the vertex form. And so by knowing that, we could tell that our vertex is at -4, -5. And since this is an understood -1 right here, we know that the parabola opens down. So that's why we know it looks like this. And so we're asking, what is the behavior of this particular function as x gets more positive? Well, as x gets more positive, the y values tend to get more negative. So here the answer to that is negative infinity. Now, when we look specifically at x equals -4, which is, let's say 1, 2, 3, 4, right here, we want to study what is the behavior of this function as x approaches -4 from both the left and the right here. What we see as that happens, the y values are starting to approach whatever the y value is for this point, which is just -5. So the answer to this question is -5. And so with this being said, I hope that this particular video has cleared up some of what we mean when we talk about a limit. I'll have another video ready that will go through how do we actually evaluate limits that are in algebraic form. And so we'll see how to do that and all the algebra that's involved. But this video was mainly dedicated to make sure that you understood that limit meant behavior, and to get an idea of what behavior actually means and some of the things that are implied in that. So I really hope this video helped. Please check out my other videos. If you need me to record anything in particular, just send me a message and let me know. Thanks. Take care.